Hey guys, in this video we're going to learn about two-part momentum problems. That is, problems that use conservation of momentum and something else, like, for example, energy or kinematics. The order in which they use these two things can flip around, right? There is some amount of variation. Sometimes you'll maybe start with the energy and then proceed to use momentum. Or maybe you'll start with momentum and then go on and use something like energy or kinematics. Just depends on the question. The specific example that I'm going to look at today from your notes packet is example 6, in which they present you with a ballistic pendulum. The idea with a ballistic pendulum is that you've got something like a bullet, usually, that's going to move forward, embed itself in this pendulum arm, and then the pendulum arm swings out to some particular height, and then you are able to measure the angle to which it moves, and from that information, figure out how fast the bullet must have been moving in the first place. This is really the only way that they had before things like photo gates and fancy kinds of sonar equipment to measure the speed of something like a bullet, because it's otherwise just too fast to measure. The first part of this question just wants to know what type of a collision this is, to which the answer is it's perfectly inelastic, simply because the bullet embeds itself inside of the pendulum arm, and therefore after the collision they move along together as one object. Now, the key thing to remember about a perfectly inelastic collision is that energy during the collision is not conserved. So the bullet's got some amount of kinetic energy that it starts with, and then after the collision, the system, consisting of the pendulum arm with the bullet stuck in it now, has some final amount of kinetic energy, but those two energies aren't equal. In fact, in most circumstances, you'll find that something like 98% of the energy that was initially present in the bullet is lost. So that means that we can't do something like as stupidly easy as saying like this energy equals the final gravitational potential energy of the system. Doesn't work that way. There's a break right here, boom, at the moment when there is a collision where there's a whole bunch of energy lost as heat and sound and deformation that prevents us from in any way relating these two quantities of energy. So there's no relationship between those. There is, however, a relationship between the final kinetic energy after the collision and the gravitational potential energy that the system has after the collision, in that however much kinetic energy the pendulum arm has after the collision turns into gravitational potential energy when it reaches its highest height. This ends up being one of the key facts that we're going to use to solve the problem. Now, I'm going to pretend that I don't know that I'm supposed to use this fact just yet, because I want to first show you how you can't only solve this problem using momentum. So I've written down the equation for conservation of momentum. I'm going to start plugging stuff into it, like, oh, the pendulum arm is initially stationary. Also, the final velocities of the two objects are the same because they stuck together. So therefore the equation simplifies to this. And I can plug in my numbers, like the mass of the bullet and the mass of the pendulum arm. And now I'm stuck. I don't know the initial velocity that the bullet had. That's the whole point of the question, is how fast was the bullet moving? Nor do I actually know the speed that the pendulum arm has after the collision. So it really would seem like we have no way forward, right? There's no way to solve this question. At least there's no way to solve it using just this information right here, right? We don't know enough. We do, however, know the thing that I mentioned earlier, which is that the kinetic energy after the collision turns into gravitational potential energy as the arm swings up. So as long as we know the maximum height to which it swings out, we can relate that gravitational potential energy to the kinetic energy after the collision, and that means that I can figure out what the final velocity of the pendulum arm is after the collision. And if I ever get that, then I'll be able to plug it in to my momentum equation and solve for the initial velocity that the bullet must have had. Plugging in my formulas for kinetic energy and gravitational potential energy, I get this far, And I notice, okay, the masses cancel out, like that's great. But, ooh, what is the height to which it moves? The information that's provided to you is they tell you, the length of the pendulum arm is 2 meters. They tell you that it swings out 53 degrees before coming to rest. But that's not the same as like the height that it moves through, right? That right there would be the height. That information's not directly given. Now, if you recall back in the energy unit, I did present you with a formula for that. We didn't derive it, and so right now we're going to derive how you get the height of a pendulum. All right, resimplifying the diagram, right, getting rid of all the messy momentum and energy stuff. Here's basically what we want to know, right? We've got the pendulum bob, it swings up, and then we're trying to find out what is that height based on the length of the arm and then the angle that it swings through. Notice that I can label both of those segments L because that's just the length of the string or pendulum arm or whatever it may happen to be. Also now I've added in a little tick mark to indicate sort of more, more simply like where the height is exactly, right over on this side. And I've also labeled another little distance here, right, which is really like the rest of this, right? If I can figure out what that distance is, and I already know that this whole distance is L, then the difference between those is going to be this height that I'm looking for. So really, I've got to figure out what that is, right? What is that side of the sort of implied triangle there? Wait a minute, triangle. It's almost as if this is going to be trigonometry. Okay, so now, given that this is my triangle and that L is the hypotenuse and the angle is there, take a minute and think about what trig function would give you the unknown side right there. You can pause if you like and think about it. All right, now, if you thought about it, you should come up with, oh, look at that, it's L cosine theta, because that is the side adjacent to the angle. All right, therefore, it's L times cosine theta. That means then that the height would be the whole length of the pendulum, L, minus L cosine theta. Therefore, the height formula is L minus L cosine theta. All right, now that we have it, let's plug it in. Apparently, I decided it would look nicer with a cursive L, but there it is, right? We've plugged in the height formula. And now we just got to plug in the numbers. They told us the length was 2, the angle was 53 degrees. Throw it all in there. And you get that the velocity is 3.96 meters per second. Really? That's awfully slow for a bullet. That's not the speed of the bullet. That's the speed of the pendulum arm plus the bullet stuck in it immediately after the collision. And now we can plug it in to our momentum equation. There it is. We've replaced one of our unknowns. Now the only remaining unknown is the initial velocity of the bullet. And it turns out that the velocity of the bullet is 202 meters per second. All right, let's do another example with a different setup because it's not going to be a pendulum every single time, right? If it were a ballistic pendulum every time, it'd get kind of boring. So there's a variety of different setups. I won't do them all, but I will do one more example so that you just have, another thing to look at. This is not an example that's in your notes packet, but if the back page of your notes packet is blank, you can go ahead and write it down there. The idea is sort of as usual, for some nefarious reason, the physicist has launched a ball of something squishy, maybe clay, at this block here. It smacks into it. Afterwards, the block is sliding backwards due to conservation of momentum, and it travels some distance before it comes to rest. So take a minute, copy down the example, and all the details you have are up here, but that's the basic scenarios. We fire something, hits a thing, it slides backward and comes to rest, and it's going to be the exact same procedure, really, except that we aren't using gravitational potential energy. We've got to use some other concept to figure out how fast the system must have been moving after that collision. Now, before I go on and show you what to do, I want you to pause the video and try and consider yourself what ought you to do. Because this is something that I expect you to be able to figure out on a test or a quiz. And so for that matter, right now would be a good time to see if you can figure out what you're supposed to do. Okay, so pause me, figure it out, set it up, and then resume the video if you're either completely stuck or if you think you got it and you want to see if you're right. All right, resuming my work here. I decided to go ahead and start with momentum, but as you can see, we get stuck in the same spot because we don't know either the initial or the final velocity. There are multiple correct ways that we could approach the sort of second half of the block's motion to figure out its velocity immediately after the collision. You could use, for example, forces and kinematics, but I think energy is easier. So this is the setup I'm using. All right, now if that's enough of a hint to push you in the right direction, again, pause the video, see if that's good. If you already got this far or further, then keep watching. Next line down in our work would say the final energy is 0, nothing, right? It's not moving at the end. It started with kinetic energy immediately after the collision, and work done by friction would be given by that expression. The friction force is given by the expression mu mg, right? That would be friction is fun. Since we're on a flat surface, the normal force is just mg. If we were on an inclined plane, then would have to include a cosine theta in there. There would be other things different about the question if we were, say, firing something up an inclined plane. But cosine theta need not be present for this question since we're on a flat surface. All right, a little bit of algebra later. We have that the velocity immediately after the collision is 3. I appear to only be able to get the number 3.96. This is kind of eerie, but okay, that apparently is the final velocity after the collision through some massive coincidence. Now that we have that, plug it in. And it seems that the initial velocity of the ball of clay is, well, that's pretty fast. It's about like 90 miles per hour, something like that. So I don't know what did that, but wow, that was moving pretty quick. All right, now there's one other thing that I want to cover in this question, and that is another type of problem that actually was asked on the previous homework and will be asked on the next one, which is what fraction of kinetic energy is lost during a collision? Now, if they just ask you for the amount of energy that's lost, that's not exactly the same as asking you for the fraction of the energy that's lost. The energy lost during the collision, meaning, that is no longer kinetic energy, but that is now like heat and sound and there's been deformation and such, the amount of energy lost is just delta K. But if we're asked about the fraction of energy lost, that means that we're comparing the change in energy to the amount of energy that was initially present. So delta K over K initial. So just like if you were trying to find merely the change in kinetic energy, you would go ahead and calculate the initial kinetic energy and the final kinetic energy, and you would get these amounts unless I, say, hypothetically screwed up my calculations. All right, regardless, I'm going to use these numbers, all right, because it kind of doesn't matter. If those are the initial and final kinetic energies, the change would be the difference. Okay, so we lost 86.3 joules of kinetic energy as heat and sound and other things. And therefore, the fraction of energy lost is 0.909 or 90.9%. Or actually, as it turns out, if we expressed it as a fraction, it would be, in fact, exactly 10/11ths. Like exactly 10/11ths. Like go ahead and type in 10 divided by 11 into your calculator, and it's going to say 0.9090909, and that is in fact precisely the amount of, or the fraction of kinetic energy that's lost during this collision. We may at some later point discuss exactly why that is the perfect ratio that we're supposed to get, but that will have to wait for another video lesson. All right, I hope this was helpful, and I'll see you guys in class.